Okay, so binomial. There's different types of distributions: skewed distributions, symmetric distributions, normal distributions, uniform distributions, binomial distributions, right? So we're dealing with binomial. So center, shape, and spread, or shape, center, and spread. So, but down here is the table shows the possible values of corresponding probabilities for x equals. X equals the number of children with type O blood from previous examples. So from the previous example we talked about yesterday. This is binomial. We know that there were 5 kids in the family. Oops, from this question here. We know there are 5 trials. We know the probability of getting a kid with type O blood was 25%. So they made the table. So the probability that none of the 5 kids would have type O blood is 0.2730. So the probability of that 0 out of the 5 would have. Okay. The probability that 1 of the 5 is 0.39551. Probability that 2 of the kids is right there. Probability of 3, probability of 4, and probability all 5 kids have type O blood. Okay. So then they make it a frequency graph, a histogram, based off that. Okay. So we would consider this binomial distribution where n is 5, p is 0.23, and this is skewed to the right. Most of the data, I would say, is on the lower side, right? Lower side, skew to the right. So here are 3 more examples. There are 2 in the middle that are symmetric, or the first 2 are symmetric. The last one is skewed to the left this time. Here's my question. When do we know it's going to be skew, symmetric? When do we know? Here's 4 examples up here. There's 1 that's skewed to the right, 1 that's skewed to the left, and 2 that are symmetric. When do we know what shape it's going to be?
Probability.
What about the probability? You're right, yeah. What about the probability?
If it's higher, it's going to be skewed left. If it's lower, it's going to be skewed right.
Exactly. Look at the probability. Look at the probability of the first one. 0.25. It's on the lower side. Look at the probability of these 2 guys here. What's the probability of these 2 guys here? Right in the middle, right? Right in the middle. What's the probability of the last guy here? It's on the high side, right? So wherever the probability is at, that's going to determine the high points. The high points. Why? Let me ask you a question. Why is the 1 bar so high? Why is the 1 bar so high? Why is the 1, what's causing the bar for one child, to be so high compared to the rest? Or better yet, what's making 5 children barely register anything?
So is this like a limited amount of getting all 5 children with type O blood?
How do you know that?
The expected value.
The expected value. What would I expect to see? If there's 5 kids and there's a 25% chance, I would expect, we talked about this yesterday, 1 to 2 kids having type O blood, right? Does that happen every time? No. But I would expect that, right? So that's why 1 and 2 are the highest, right? Same thing with these 2 guys. I think these guys are the same thing, right? The probability is in the middle, 50%. So that's why, so out of 5, if I change the probability to 51%, now it would be between 2 and 3. I would expect between 2 and 3 kids to get type O blood, right? If I change the probability. And then if I change the probability one more time and said 80% chance, there's a 0.8 probability that they'll have a kid who has type O blood. Then you're going to expect 4 to 5 kids having it, right? So that's where the modes are. The modes are the high bars, most frequency. Okay? Because on the test, they're going to do this. They're going to give you, they're going to say n equals, I don't know, 25. P equals 0.4. And then they're going to give you 5 pictures. 5 pictures, 5 graphs like you see here. And you have to pick the one that best matches this. Best matches this. Okay? So n is the fixed number. There's 25. That means there's 25 whatever they were looking at. Where would we expect the high bars to be? Where would we expect to see the high bars at?
Like a 10-ish.
Around 10, right? Around 10. Because 10 is 40% of 25, right there, yeah. That would be just a little bit left of the middle. A little bit left of the middle, right? So we would probably see something like this. So the shape would probably be something like right? We would expect something like that. Right? That's like I said, that's what they're going to do. That's what they're going to ask you on a test. Okay? And then they'll ask you, I've seen a question too where they'll give you a scenario and they'll say, is it binomial first? So you got to decide yes binomial, no binomial. And then if it is binomial, you have to pick the picture. You have to pick the picture. So you have to be able to say, if it's binomial, which picture? Or if it's not binomial, there was going to be no picture. Okay, this is only for binomial distribution. So if I have 25 total, 0.4 is my probability of success. What is 40% of 25? 10-ish, right? So the high bars would be around 10. Okay, high bars would be around 10. All right, okay. We talked about this, expected value. These two are also given. These two are also given to you on the formula sheet. Your formula sheet, these two are given. Okay, so you don't have to memorize any of these guys because they're given to you. You just have to know what n is, k is, p is. Okay? Okay, so expected value. Expected value, how do you find out? Well, you take n and multiply it times p. N times p, which you did, right? Which you guys have been doing. Standard deviation is spread. That's got another formula, okay, which is on your formula sheet. Formula you don't have to memorize. You just have to know how to identify and use, okay? So if they're talking about binomial distribution and they want to know about center, use the expected value. If they want to know about spread or variability, we're going to use the standard deviation formula, okay? If they want to know about shape, then you kind of just use one of these guys. You kind of, where's the peak? Where's the peak going to be? Is the peak going to be in the middle, like these two guys? Is the peak going to be on the left side, or is the peak going to be on the right side? And then you determine from there. Okay? All right, so let's look at number 7. Number 7 on the next page. All right. Okay, so assume that each of the 21 students in Mr. Hogarth's AP statistics class who did the bottled water versus tap water. So the challenge was, I used to do this pre-COVID, where I'd bring in 2 bottles of water that were unlabeled. One was from the tap water, and also when we could have tap water out here. So just water from the water faucet. And one was bottled water, came from bottled water. Okay? And I would test students to see if they knew. So come up, have one, have the other, and then you guess. I think it's this one. A is the tap water. B is the bottled water, or vice versa, whatever you want. Okay. This class did the same thing. So there was a 1/3 chance of each student identifying the cup containing the bottled water correctly. Okay? X is the number of students who actually made that choice. Right? So how many students actually made that choice? At right is a histogram of the probability. Okay? So they show the probability. So they want us to calculate and interpret the mean of X. Okay? Well, the mean is N times P. All right? So we're going to write the formula we use. The mean or expected value is N times P. What would N be in this case? 21. What would P be in this case? 1/3. 21 times 1/3 is 7. Where is the highest bar? Where are the highest bars centered around? Makes sense, right? That's what we would expect. We would expect about 7 students to recognize that this is the bottled water, not the tap water. Okay? So that's how we interpret it. We would expect 7 students to guess the bottled water correctly. Standard deviation. Okay, that's the spread. We're going to use this formula down here. Okay. Actually, what we should have done, did it say it was binomial distribution? What we should have done at the very beginning was decide if it's binomial or not. We skipped a step because it might not be binomial. If it's not binomial, we can't do any of these things. So let's go back to that. Is this situation binomial? How do we know?
Either they guess whether they guess correctly or not.
Okay, so guess correctly or not, guess bottle or not. Independent? So if one kid goes up there and drinks water and says, I think that's tap water, is that going to affect what the next one's going to do? No? Okay. Number of, fixed number of trials? 21. And last one is the success always the same probability? 1/3? Okay. That's what we should always do first. I just skipped that part. Okay, standard deviation.
So in order to like do these formulas, we need to figure out if it's binomial first.
Yeah. Because these formulas only go with binomial distribution. So to use them, we have to make sure it's binomial distribution. Definitely check that first. Okay. Well, N times P we already know because we just did that one. N times P is 21 times 1/3. Times 1 minus P. 1 minus P is just everything else. Okay, so if I multiply, let's see, those cancel out, so I get square root 14 over 3. Multiply straight across, 14 over 3. So then you go to your calculator. I could just do it here. $14 over 3 is 4.666666 forever. So now I'm going to take the square root of that. Oops. So the square root of my previous answer. I get, why isn't it showing up? Here we go. 2.160. 2.160. Okay. What does that number be? That's a half credit answer. What's the full credit answer? Full credit means correct interpretation along with in context. So telling me context, just like I did with the first one. I explained what it meant, expected value, bottled water, correctly. Okay. So what is the full credit answer? Yes. Exactly. Exactly. We would expect 7 students to guess correctly. That number will vary by about 2.16 students. That is the 3 out of 3, 4 out of 4 answer. Okay? So we would expect 7 students to guess correctly. That number will vary by about 2.160 students. That's why the bars around 7 are high as well, because there could be some vary. There could be some leeway there. Okay. Okay, last one. In a survey of 500 US teenagers aged 14 to 18, so every single person except for me in here, this is talking about you guys. Okay, 14 to 18. I don't think we have any 19-year-olds, super seniors. Subjects were asked a variety of questions about personal finance. Okay. One question asked whether teens had a debit card. Okay. Suppose that exactly 12% of teens from 14 to 18 have debit cards. Okay. Let X be the number of teens in a random sample of 500 who have a debit card. Use a binomial distribution to estimate the probability that fewer than 50 of those 500 teens have a debit card. Okay? So there's a what percent chance? What percent chance is there that a student or that a teenager has a debit card? 12%, okay? So is this, or it says use binomial distribution. So we really don't have to check because it says use binomial distribution. When it says use binomial distribution, actually, you know what? There's a typo there. Instead of binomial, it's supposed to be normal. There's a typo there. It's supposed to be normal. Use a normal distribution. So now that's the case, we have to check to see if it's binomial. So is this binomial? Is it binary? Is it independent? Is there a fixed number? Is there the probability of success always going to be the same? So what's the probability that one of the 500 has a card? What's the probability that a random student from 14 or random teenager from 14 to 18 has a debit card? 12%. Okay. But it's 50. So does the probability change?
Since the sample size was divided by 10, should we divide the probability by 10?
No. No, that's not how it, because then it wouldn't represent. No, I'm asking, is it binomial distribution? I heard like 5 people say, yeah. But I asked the question and no one answered it. Maybe we'll have a quiz on Friday. Ooh. Answer now or answer later? No, that's what Ickman was saying. No, because, so for example, if, let's say, there was just an election. So let's use an election. Something like 70% of Californians voted for Gavin Newsom for governor. 70%. 7 out of every 10 people. If I took a sample of just Fresno, would I divide that probability or that percentage? I would. It's still 70%. It's still 70%, right? So it doesn't matter if you take a sample. If you take a good sample, it's still going to stay the same probability. Okay, it's still going to stay the same probability because California or Fresno has roughly 1 million people. Voters probably half that, if that, probably 30%. So let's say 300,000. There's 35 million people in California. So you would have to divide it by 70. So if I divide 70% by 70, you're saying 1% of Fresno voted for Gavin Newsom? If 1% of Fresno voted for Gavin Newsom, he wouldn't have won. Okay? It's still 70%. It's still 70%. That percent's not going to change. Okay? Because if they did the sample, if it's a random sample, it would be the same. My question is the glasses question. That's my question. The glasses question. The contacts question. What did we say there? Why theoretically no? This question, where is it today? This question right here. Isn't it like this question?
Because this question is asked to.
Ooh, maybe we will have a quiz on Friday. On binomial distribution. So my question is, the question you're looking at right now, number 8, isn't that like number 4? And we said no, didn't we? So how do we do it? No, I'm saying this is a no, right? This said no. binomial distribution? No. So how can we say this is binomial distribution? The one you're looking at right now. The one you're looking at your paper right now. How can we say that one is binomial when that one was not binomial and they seem the same? Or is there a difference? What's the difference? So, the question you're looking at right now says there was 500 teenagers. They got a sample of 500 teenagers. 12% of them have debit cards. This question says there's 1,500 workers. 66% of them have glasses or contacts. Those sound like similar situations to me. Normal distribution. To use, that we're going to use that eventually when we get to it, but we have to show that it's binomial before that's what we're going to do next. What we're going to do next is that. We're going to use the normal curve, draw, label, shade. We're going to do that. But before we can do that and our answer be correct, we have to determine whether it's binomial distribution.
Wouldn't it be binomial distribution?
Because
there's two. The B, we determine whether the teenagers have debit cards or not. The second one, it's independent because it doesn't affect the other teenagers. It only affects that teenager who has a debit card or don't have a debit card.
Okay.
And then there's a fixed number because we're having a fixed sample of 500.
Okay. So what about probability? But see, the argument you're giving me right now would work for this guy. And why was this guy no? That's what I'm saying. Every argument you guys have given me, I buy, but it didn't work for this one. What changes? Well, wouldn't the other probability change? Okay, so this one was a no because the probability changed, right? Okay. So let's go back to the one you're looking at right now. Will the probability change here? Yeah, this one seems like it'll change more. So this one should be an even bigger no, right? No, the answer is no. No, the answer is no, it wouldn't change. Why not?
Is it supposed to be exactly 12%? Is one of the probability be 12%?
Yeah, it's saying 12%. Just like the other question was 66%. The other question had 1,500 people. This question had 500 people. If I choose one of them, so what's 12% of 500? 60. Okay, so our expected value is 60, right? I choose one person. I have 59 now. 59 out of 499. 59 out of 499. What's that probability? Okay. If I keep doing that, so 59 out of 499, 58 out of 498, would it affect the probability? We're getting to 50. But why does that not matter in this question? That's my question. Why does that not matter in that question? If you think about it, it'll figure it out. But I think some of you guys are just waiting for me to give the answer, and I'm not going to. Yeah. You're getting close. You're getting close. Where does 600, or sorry, where does 66% come from? Okay. Where does 12% come from? Does it come from the 500 people? If it came from the 500 people, we have the same question. But where does the 12% come from? That's my question. Where did they get that 12% from?
Apparently all the teenagers combined.
Millions, right? Millions. So we're not talking about 500. We're actually talking about millions. So if I take one away over millions, it's not going to matter. It's still going to be 12%, right? So we're not talking about 500. That's why this is a different question. 2 words, population versus sample. This population is everybody from 14 to 18. Everybody from 14 to 18. You're talking about 100 million people, 50 to 100 million people, right? The other question here, where does that 66% come from? Just the office building. That population is a lot smaller. If the population is really, really small, then yeah, it'll affect. But if the population is huge, it doesn't affect the probability. That's the reason why it's binomial, okay? That's the reason why it's okay on the problem we're going to do, but it wasn't okay here, okay? Who is the population, right? Who is the population? Is it small where it's going to affect, or is it large where 1 person, 2 people, 3 people won't put a dent in anything? If I got 5 more people to vote for whoever ran against Gavin Newsom. Let's say I got 5 more people. Oh, these 5 people forgot to vote. They're going to put a vote in for the other guy. Would that change anything? No. Gavin Newsom would still win by 70%, right? Because there are millions and millions and millions of voters in California. Okay, that's the difference, right? If it was central, if it was senior class president, right? And I said, these 5 people didn't vote. They're going to vote for this person over here. That might change things, right? That might change things. That's the difference. You're talking about a population size that's very small versus very big. Okay? Okay, so what I got me that last thing you're going to do. Find me the mean, find me the standard deviation. What's the standard deviation going to be? Because we're going to use that tomorrow. We'll finish the question tomorrow, but I just want you to find me the standard deviation. Because we're going to mean standard deviation to use normal distribution. So just go 3 places if it's a big number. The mean standard deviation, we already got the mean. The mean 60.
6.33.
So the mean was n times p, right? N is 500. P is 0.12. Okay. So what was it?
6.33.
Let's see. Give me 1 second. So we got square roots. We got, what was it? 500. N is 500, right? Times, what was it? 0.12. And then 1 more. 1 minus that, which is 0.88. 7.266. 7.266. I had it written down wrong. I had 60 in here for some reason. That's not N. 7.266. Okay, we'll finish this one tomorrow, and then you're going to do that. You'll work on that tomorrow. It's not assigned yet. The worksheet is not assigned yet, so don't worry about it. I'll assign it tomorrow. I just wanted to give it to you today so I didn't forget. Okay?